Critical infrastructure, power grids, water treatment facilities, and manufacturing plants are currently the primary targets for the world's most capable cyber threat actors. The supervisory control and data acquisition systems, or SCADA, that run these facilities were originally designed for absolute physical reliability. They operated in complete isolation, protected by an air gap that separated industrial control systems from the outside world. That air gap is disappearing. Operational technology, or OT, is rapidly converging with standard enterprise IT networks to allow for remote monitoring, predictive maintenance, and real-time data analysis. Here is a modern industrial facility. On the left, IT data flow, like servers and business applications. On the right, the OT layer, actuating physical valves and turbines. Connecting them allows digital threats to cross the boundary, turning a network intrusion into a physical event. Nation-state actors and sophisticated cyber criminals actively exploit this exact bridge to hold physical production hostage. Securing this infrastructure presents an immediate operational paradox. Security teams must identify and patch vulnerabilities in these systems, but running standard IT vulnerability scans on fragile industrial hardware can crash the systems and disrupt critical processes. The solution is a specialized SCADA and ICS assessment methodology. It combines tightly constrained automated scanning with expert manual testing, specifically engineered to operate safely within sensitive physical environments. In a fully connected facility, industrial network auditing secures the physical infrastructure and human lives behind the digital data. To secure an ICS environment, we first need to map its architecture layer by layer, locating exactly where the legacy vulnerabilities hide. This layered network topology diagram builds from the mechanical floor upward. At the very bottom is Layer 1, the physical control layer. This consists of programmable logic controllers, or PLCs, and remote terminal units, or RTUs. These devices translate digital commands into actual mechanical force. Hardware at this layer is highly susceptible to exploitation. Security assessments consistently uncover outdated firmware, default factory configurations, and inherently insecure ladder logic governing the machines. Moving up, the diagram introduces Layer 2, the supervisory layer. This houses the SCADA server and the human-machine interface, or HMI, which human operators use to send instructions down to the physical layer. Assessors targeting this layer test for unpatched software, exposed access credentials, and insecure remote access points that operators rely on for maintenance. Every supervisory tool added for operator convenience actively multiplies the attack surface of the heavy machinery sitting below it. If we isolate the data pathways in this diagram, we see the connective tissue of the architecture, industrial communication protocols like Modbus, DNP3, and OPC-UA. These specific protocols were engineered decades before modern cyber threats existed. They operate on implicit trust and lack native cryptographic authentication. The data moves entirely in the clear, completely transparent to anyone on the network. This design invites severe protocol attacks. An unauthorized user on the network can easily execute spoofing, replay attacks, or man-in-the-middle interceptions, silently overriding the HMI's commands. The danger peaks at Layer 3, the enterprise IT-OT convergence point, where firewalls, DMZs, and data historians sit. When facilities integrate cloud-connected components and remote access gateways at this layer, they inadvertently expose those unauthenticated industrial protocols to the wider internet. Relying on the legacy trust model of industrial protocols makes modern IT connectivity inherently dangerous without specialized, layered defenses. This brings operators to a critical decision point. How do security teams map these protocol flaws without causing physical downtime? Deploying aggressive, automated IT vulnerability scanners inside a fragile operational environment will shatter operations. Standard black box IT testing relies on active ping sweeps and forced packet injection. In an OT network, this volume of traffic can overwhelm PLCs, crashing the hardware and halting safety-critical production entirely. The required alternative is a strict 6-step OT assessment methodology tailored for industrial fragility. Notice that the first two phases operate entirely in a passive, safe mode. Step 1 focuses on scoping and requirements. Before a single packet is analyzed, teams must define safety protocols, build a complete asset inventory, and establish strict rules of engagement. Step 2 is discovery and reconnaissance. Assessors map the PLCs, RTUs, and communication protocols by quietly listening to network traffic. They observe the environment without ever injecting disruptive active signals. The earliest phases of a proper OT assessment prioritize zero-impact connaissance. Zero-impact observation is a functional requirement of industrial security. Only after the environment is mapped does the assessment move into highly controlled active testing. Step 3 involves executing simulated exploits to test authorization bypasses and identify firmware gaps. Crucially, these active tests occur strictly during pre-scheduled operational downtime. For SCADA environments, white box testing, which grants complete architectural transparency, or gray box testing, which simulates an insider threat, are heavily preferred. They allow assessors to find logic flaws faster and safer than zero-knowledge approaches. Step 4 is analysis and reporting. Every discovered flaw is evaluated and assigned a strict severity rating, prioritizing critical physical risks over low-level software bugs. Step 5 delivers remediation guidance. OT teams receive actionable patching guides, firmware update steps, and robust network segmentation strategies. Step 6 closes the loop with verification. Assessors retest the modified controls to mathematically prove the industrial environment is secure. Executing this 6-step lifecycle requires elite personnel. Standard IT staff cannot safely navigate ICS architecture. Organizations rely on industrial cybersecurity specialists holding certifications like GICSP or OSCP to ensure operational safety. True remediation in an industrial context must safely bridge the gap between digital patching and physical system integrity. Beyond operational safety, these rigorous assessments are required by strict regulatory mandates. Industrial security frameworks like IEC 62443, NIST Special Publication 800-82, and NERC CIP actively require organizations to validate their OT security posture. Maintaining compliance demands an annual baseline assessment at minimum. For highly critical infrastructure, or following significant system upgrades, that cadence scales up to quarterly reviews. This diagram illustrates a successful assessment lifecycle. It secures the DMZ boundary at Layer 3, patches physical hardware vulnerabilities, and locks down data pathways. This intelligence directly informs incident response, ensuring the facility withstands targeted attacks. Partnering with specialized security teams to identify these hidden hardware and protocol vulnerabilities ensures that legacy operational technology can survive a modern digital threat landscape. In the industrial realm, a proactive, strictly constrained digital defense is the absolute foundation of physical safety and operational continuity.